get nitrogen and other nutrients for their own demands, and in the same process, the trees take up whatever it needs. And this is another strategy that the trees are giving carbon but not giving nitrogen, not at the leaf level, not at the roots level. And that indicates that there is a high demand for nitrogen in the system. We looked at the root branching frequency using those images, and you could see the high frequency of root branching. This is fine roots which try to explore the unexplored components of the soil up to a meter depth to find wherever they could reach out to seek nutrients. So that's another indication that the trees are investing carbon and growing more roots to reach out to the resources that they need. And a more comprehensive data of those fine roots is presented here. I don't want you to go into those details because soil has layers, O horizon, A horizon, and B horizon. So these are layers. So it's not just a bulk of mud or dirt, but it's organized into certain layers, and each layer has its own specific characteristics. But there is a significant increase of fine root biomass in the upper soil layers, and this is your majority of the organic matter is in the resources available. But up to a meter depth, they are going now seeking nutrients there. As I said, the lateral pulp reduce the nitrogen content as a nitrogen conservation strategy. And the carbon exudation increased. And with that increase, the mineralization of organic matter to release nitrogen back into the available pool so that the root would take it up. It's relatively higher, 47% more across the whole range of studies. We did that studies and our PhD student did the field studies using isotope levels. So 47% increase of the available nitrogen in the soil environment for the trees and microbes to take up. The same student looked at the response ratios of elevated CO2. And there's a whole range of processes. Which process goes up, which process goes up. We don't know how, but the trees are priming this process, net mineralizations, to release more nitrogen and ammonia. But they are really suppressing this process, nitrification. This process, when it happens, it releases nitrogen and bacteria could use it. It could leach out of the soil. It could go into the air as nitrous oxide gas. So trees are somehow exuding a chemical in the exudates that is suppressing this process. So this is our next frontier question. What is that particular chemical, and can we simulate and synthesize that chemical in the lab to see if this is really the case? So we did metabolomics, and one of our research fellows is looking into this. But again, we see suppression of this process as a nitrogen conservation strategy. Quite smart for these old trees. The same student looked at the month-to-month responses of this nitrogen mineralization as an indicator of nitrogen availability. And overall, over a year, it increased 28 kilograms more nitrogen to be available to trees compared to the ambient levels. And this is closely linked to the soil, dissolved organic carbon, which is exudates, and the carbon that the trees use on the soil. So this is how it's driving this process. While nitrogen availability and other nutrients are enhanced, what happens to greenhouse gases? So we have nitrous oxide, and 60% of the global nitrous oxide gas, which is the laughing gas. And that is contributed 60% by the forest globally. It's 310 times more potent in inducing global warming than carbon dioxide. Similarly, methane is about 84% is taken up by forests. So methane is uptaken, which is a climate service. Nitrous oxide is produced, which goes up into the air, causing global warming. So these are opposing processes, positive and negative feedbacks to global warming. And so we wanted to know what happens to those. So we have automated robotic greenhouse gas measurement systems which continuously measure the exchange of carbon dioxide, methane, and CO2. And my PhD student Alex is explaining his automated systems. So at the same time we measure, and the data is downloaded every day, so they could access the data from the campus to see what's going on. Here is methane. This is the zero line. So anything below the zero line is a consumption of atmospheric methane into the soil. The microbes eat the methane for energy. So there is more consumption in the controlled soils than in the elevated CO2. So the ability of the biomes to consume methane is reduced. We think that higher nitrogen availability usually suppresses this process. So I'm not going to go into this detail unless you are a biogeochemist. But this is something we need to account for, the net carbon balance, what comes in and what goes out in terms of global warming potential. And this is the first time we're doing it at this scale and at this resolution in data points in this forest anywhere in the world. Similarly, nitrous oxide fluxes, it's just above the zero. So forests produce nitrous oxide, the treatment plants are producing less nitrous oxide than the control one. So when we have this surface here, we have a surface here, climate mitigation surface here. And it also indicates that the trees are using more of the nitrogen, the microbes will conserving, and it's really suppressing this nitrous oxide emission capability of the forest. And if we account for their global warming potential, then we could see the net carbon balance to really allow the IPCC to have a more accurate predictions of the role of forest in mitigating climate change. I'll come to my concluding slides. So what we have seen so far that the mature trees are able to gain more biomass, but how long? In the first 7 years, it's going up, but there are other factors that might be affecting. If there is a drought, carbon goes down, there is a hydraulic pressure on the trees. If there is warming, that could also affect the allocation in wood formations. And these are climate extremes that we experience these days everywhere. So doing the long-term experiment will enable us to look at the year-to-year variations in these other climate extremes and tweak it around elevated CO2 to come up with more robust estimations. And we need more of these measurements. So with Muhammad Praz, who visited early this year, we discussed to mount cameras overlooking these particular experimental arrays, multispectral cameras, right? So worth of about 30,000 pounds that we just buy, and it will look at a treatment in a control array, to look at the deep greenness, water stress, chlorophyll content, and so on. But I am not the expert, so Muhammad could tell you more if you have further questions than this. So we will be installing those cameras and sending the images back here to NUST to look if there are changes. There are some diseases in the trees, and it might be that we could pick up those diseases in the leaves by those image analyses. For nitrogen, trees are conserving nitrogens while allocating more carbon below ground. Nitrogen supply is enhanced, but the soil nitrogen resource is not unlimited. So it might be exhausted. If we don't fertilize these plants, there might be a nitrogen limitation of this response. When will this happen? We don't know. And this is why we're going into the second decade of this experiment to really find out if there is a nitrogen limitation of the system. And there are significant changes in the magnitude and direction of greenhouse gases, and we need to account for those processes. And it is for these reasons, how long is long enough in an ecology research? It's a very challenging question, but we're going into 2030s to be able to address some of those. And this would be the first of its type to do this experiment for 2 decades. But we were lucky enough to be given the funding by a charity, not the government, to continue. So with this, I thank our funding partners, both national and international, and our international collaborators across the globe. I should have put the University of Bath here. I didn't get the time. The many researchers and technicians and visiting students who contribute to the research. So I would like to acknowledge them, and then Muhammad Praz for inviting me to work with you. And if you see any potentials for research collaborations, here is my email, so don't hesitate to contact me. Thank you. Sorry, I went a bit over time. Do you have any questions?
You are giving some external inputs to the forest, and they are behaving and analyzing them, that's how they are behaving in response to that. So over the years, maybe their genomics may evolve to handle these external factors. So are you looking at that as well, or you are just looking at the environmental inputs and not genomics?
We're doing the genomics, so our geneticists are looking at the prevalence in the genetics, metagenomics, everything in there. And one of the projects that I mentioned, which looks at the memory of trees and transmitting awareness to the young ones in terms of disease. So that's a key methylation process in the DNA, which protects these trees from those particular diseases. And that methylation process is significantly changed in response to elevated CO2 and the conditions that they are experiencing in the moment. So yes, we do. We look at the metagenomics of not only trees but everything from microbes to insects. So we collaborate with some global leaders where we trap all the insects and we look at their metagenomics as well.
Sir, one more question, not related to this, but I think it is relevant to your expertise. Basically, it is said that there is a certain percentage of organic matter that should be in the soil to classify it as fertile soil. However, the quantity of organic matter present in the Pakistani soil is significantly less as compared to what is being classified as organically stable soil. However, it has been very aggressively portrayed that our soil, Pakistani soil, is very fertile. So, is it just you can say that it is technically incorrect to say that our soil is very fertile, or is there some other?
The fertility of soils depends on the climate of the regions and how we use it. So in Pakistan we use excessively, and because of firewood limitations, people collect all the organic matter to use it in the open. So from crops to everything, and that's organic matter. It should end up in the soil, but it ends up in our cooking stoves. So we really exhausted the amount of organic matter, which is the base of nutrient supply in the health of soil. So the health of soil is degraded because of intensive agriculture. But there are ways that we could recover there. And the arid zone, semi-arid zone will have low soil fertility in terms of organic matter, say in the agricultural data of Punjab. But then if you go to wet areas, like in the northern areas, where the temperatures are low, decomposition are low, so you can see higher organic matter. So it depends on the region. But when I think of Pakistan, it's just that we are poor using our soil resource, and we don't replenish the health of the soil. And if we start doing it, the prices of crop production will increase, but no one is able to pay that price. So in the UK, we advise the government on how to maintain soil fertility. I sit on that advisory panel, and we have incentives for farmers. When they do environmentally friendly practices to improve soil health, they get money for that, because they cannot raise the price of the milk or the dairy products. They have to compete with European markets. So the government is paying the taxpayer money to the farmers to enable tree plantations with soil health recovery. But here, probably the scale of the economy is such that the government may not be able to subsidize the farmers to build our country.
I have one question, Professor.
Yeah.
First of all, thank you for such a nice presentation, and I felt so connected with the nature after listening to all this. So, you're collecting your research team and all the network, we are collecting so much of the data for like few years. So, is this data also available, publicly available to research? Or if not, you are not, publishing your own data. So, are there any, sources from where, as a, because we are, as a AI researcher, we are hungry about data. So, can you recommend such data publicly available?
We have a dedicated data officer which archives all of our data. And some of the data is embargoed for 2 years or 3 years before it gets published. But we have a commitment to the UK government. When they fund us, we have to make that data publicly available. So parts of those data are freely available. If you are interested, I could connect you with our data officer, and who could guide you to the particular data sets. But with time, we have a commitment to be a global repository of base data. So the government is also interested for us to not only store and share our data, but store and share the data from other experiments like Australia and Amazonia. So in the near future, majority of it will be available. And this is our commitment to the government, and we have to do it. So one project finished, and I have to load up the data to government sites as well, in addition to ours. But ours will be available, and we encourage engagement of researchers from AI or image analysis or any other utilize our data to ground truth some of the observations that we have so far.
Since forests are living organisms themselves, they will probably adapt themselves over the years as well. We are seeing their response to elevated CO2 territory, but will they be responding in a similar manner after 30 years or 50 years to the same elevated CO2 level?
Yes, they will be not only elevated CO2, but the moisture or heat events, and what is the threshold of the leaf in terms of the temperature, because the air temperature is about a degree lower than the leaf temperature. So we using some sort of a cameras to measure the leaf temperature. So these are thermal cameras. One of the PhD students will look here. So they are adapting. And these trees, when they were planted 198 years ago, the CO2 concentrations were much lower. So they are able to adapt and survive. But what would be the implications of those adaptations for carbon, specifically the environment? But here are biodiversity implications. We see changes in the pollens, which the bees and the insect seeds. And we just published a paper last week where the change of the chemistry in the pollens might be affecting bees population. So we're looking at the whole range of these cascading effects of these global changes.
Also, one more thing, you showed a graph which showed that forests had an increase in the net productivity with elevated CO2. So is there some saturation limit to that increase, or will the net productivity keep on increasing?
There might be some stable shift responses, but we're not sure because the current 10 years is not enough. So they might be optimizing photosynthesis. So this is what plants do. They optimize photosynthesis to capture more carbon. But if there are other stressors, it might constrain it. But when you give them the resource, they are able to optimize it. Like our agricultural crops, we give them fertilizer and you see more growth responses and more productivity. They will continue to capture that unless there is another limitation that kicks in to affect their survival of photosynthetic activities.
Paddy rice or rice crop, that is actually one of the major sources of methane in summer. And there are not really measures to capture that methane. So, any recommended practices or policies?
So South Asia particularly are relying on groundwater. So we have these tube wells in water pumps and everything just to grow rice. But the rice is a key anthropogenic source of methane. The amount of methane it produces probably the tree would not be able to capture it all. That's one thing. But the alternatives are to look at alternate flooding and drying, because rice don't need to be under flooded conditions all the time, because the flooding causes the methane emissions. So I had students from India who grew in some of the rice with alternate flooding and drying and with continuous flooding, and we looked at these greenhouse gas exchanges. But there are trade-offs. Alternate flooding and drying resulted in low biomass production than the continuous flooding. But then there was greenhouse gas emission reduction benefits, particularly methane and nitrous oxide. So unless the governments are able to pay for the true price of environmentally sound rice, we would have these issues of methane emissions from rice. But there are these solutions that help to reduce methane emissions. Start now. Thank you.
Thank you so much, sir, for that insightful and thought-provoking presentation. I would like to extend our heartfelt thanks to Professor Dr. Samiullah for such an comprehensive and enlightening seminar. Your research and expertise have provided us with the invaluable awareness regarding the future of forests and their critical role in our environment. Thank you all for your participation and for making this event a success. We extend a special thanks once again to Professor Dr. Samiullah for his time and insights. With that, we conclude our today's seminar and look forward to continuing these important discussions. Thank you and Assalamu alaikum.